Okay, so sorry for the delay and good afternoon, everyone. Let's get it started. So, few things today which I'm going to discuss in the graph theory. Maybe let me list down them. So, one is the hand-shaking lemma. Shaking lemma. Then we will talk about Euler's Euler's graph, Euler's graph and Hamiltonian graph. Okay, and then we will see graph coloring in a bit detail. Okay. So these are the major three topics which we are going to cover today. So let's get started with hand-shaking lemma. And very important and fundamental lemma, hand-shaking lemma. And hand-shaking because it has the connection with shaking hands in a group, right? So in, let's say, if there is a gathering, only like shaking hands can be considered as a edge in a graph, and each individual person are nodes, right? So when you shake hands, you actually cannot shake hand with one person, right? So you shaking hand means there is always two person involved. Anyway, so the theorem says any simple graph, right? For any simple graph, sum of degree for all the vertices in the graph is 2 times number of edges. Okay, so for any simple graph, sum of degree for all vertices in that graph, in the graph, is equal to the number of is 2 times number of edges in that graph. What does it mean? Can we write it mathematically? So let's try to write it. So let's call it U belonging to vertices of G and degree of U, right? So this is what? Degree of every node. Sum of all that is 2 times number of edges. Okay, and this is true for any simple graph. What do you mean by simple graph? A simple graph is that graph which do not have multiple edges between one's like pair of nodes or pair of vertices. Only one edge is allowed between a pair of vertices, and there is no self loop. Okay, so if these are the conditions, then this theorem is true. And let's try to like understand with an example, or then we will try to prove it. Okay, so what it is saying is the hand-shaking lemma. Let's say this is my graph. Okay, very simple graph. Now this, or maybe slightly like this, any graph, right? So this is my graph. Now what is the number of edges here? 1, 2, 3, 4, right? Number of edges E of G is 4. What is the sum of degrees? What is the degree of this particular node? First node, this one. Let me, this one, what is the degree? Anyone? Of this node? 8. 1, right? Yeah, this one is 1. This one is 1, 2, 3. This is 1, 2, and this is what 2, right? Each of these has degree this. And the sum of degree, right? So the sum of degree of U, where U belongs to PG, is 8, and you can see that that is double the number of edges, right? And this is not only true for this particular graph. Actually, this is true for any graph. If you sum the degrees, that comes out to the same as number of edges. How do you prove it? Can we use a mathematical induction to prove it? If we can prove using mathematical induction, what is the n here, right? So we usually have something called p of n, right? So what is n here? Maybe n can be a number of edges, right? So that's a simple thing. So we can assume that n is the number of edges, and the pn is, let's say, suppose n is number of edges in the graph, then this is nothing but 2 times, oh sorry, not 2 times, the sum of degree of U is 2 times n PG, right? So now if there is Pn is a predicate, suppose n is this degree and then this is true, right? So this is the statement, right? Predicate n. So P of n is a predicate n, and this is what is it should be true for now one edge, right? Or let's say 0 edge. What is P0? P0 means the base case is P0. Right? P for predicate. So this is the predicate which is we are saying it for some number n. Now with this n we will show that P0 is true, and then P0 then we say that if P0 is true, then we will assume that Pk is true, and then we will say P of k plus 1 is also true, right? We will show that like that. So P0, what do you mean by P0? P0 means a graph without having any edges, right? So a graph without having any edges, like this graph, right? This is a graph with 4 nodes here, shown here by 4 circle, and this has no edge. So any number of edges, we don't really worry, but number of any number of nodes, we don't worry, but the number of edges is 0. So in this case, what is the sum of the degree? What is the sum of degree? Sum of the degree in this graph? Anyone? 0. Right? So trivially, the statement 2 power 2n is trivially true, right? So that's this statement P0 is true, you can say. You can also verify it for P1, right? Maybe just to verify, because P1 will be what? A graph having only one edge. There might be more vertices, we really don't care, but the number of edges is just 1. So the sum of degree here will be 2, right? For P1, the sum of degree is 2, because here there is 1 degree, here there is 1, all others have 0. So therefore, sum of degree is 2, and number that is 2 times number of edges. Just to prove so sure, like, so P0 is true, P1 is true. Also, you can assume that P of k is true, right? What do you mean by P of k is true? P of k is true means if the graph has k edges, and then this is true, right? So the sum of degree is 2 times the number of edges, 2k. Now, what we need to prove or show that P of k plus 1, whether this is true or not, right? How do we solve it? So let's say pk is true, right? That is, we have assumed already. So that means, let me write it. So degree of all u belonging to b of g is 2 to the k, right? This is, we have already assumed that this is true. Now what we will do is we will add one edge in this particular graph, right? Which has, the graph has k edges. Now what we will do is we will add one edge. So let's say this is a graph. Any graph, any random graph. Now what we are trying to do is we will add one edge. So once we add one edge, right, in this graph, the number of nodes are fixed. Let's say, case one is number of nodes are fixed. Case two is you also add one node, but case one, let's say number of nodes are fixed. Then what will happen? That sum of degree. Right? So let's say I added a new edge using red color, like this, right? So once I add this edge, the degree of this guy, right, this guy will be increased by +1. Degree of this guy will also be increased by +1. So total increase in the degree will be +2, right? And that's what we want actually. So this is degree when we have just the number of vertices, right? So this will be like +2. This whole quantity will be increased by +2, right? So when we increase an edge, then an increase in the sum of degree is +2, and that is same as saying that 2k plus 1, right? So that is 2k plus 2. Right? So both sides +2 increase. So that is when you increase an edge, that sum of degree is increasing by +2. Similarly, you can see if I add another, like this could be a possibility that my graph is increased. Let's say this is my graph initially. Now my new graph is, let's say, contains one extra edge and one extra node. Even in that case, right, the degree will increase +2. So any case, when you go from k edges to k plus 1 edges, the degree will increase by +2, right? So therefore, the p of k plus 1 is also true. P of k plus 1 is also true. And that's what the proof, that's completes the proof, because we have said that base case is true, and we have said that if pk is true, pk plus 1 is also true, right? So that's very trivial, like you can understand this theorem. Okay, so this is called handshaking lemma, and this is called handshaking lemma because for every handshake you need two people, right? For every handshake you need two people. So if I consider this as a handshake, you need two people. If I consider this as a handshake, you need again two people, right? So that way, this is true for any simple graph, right? So when I say simple graph, a graph without self loop and a graph with only one edge between two nodes. Right? So for example, this is not a simple graph. Or even this edge, not a simple graph. These are not simple graph. Okay. So this is for just for the simple graph. Okay. All right. So next, now let's look into something called Euler's or called Eulerian graph. Okay. So what is an Eulerian graph? A graph is called Eulerian graph if, right, if all the edges exactly once. What does it mean? Right, and it should be connected obviously. So this is like, let's say this is a graph, no? Now this graph is not an Eulerian graph. Why this is not an Eulerian graph? Because if I start visiting, right, so let's say I visiting like this, I go to this, and then I go to this, and then I go to this, and all the edges exactly once, and you should and you should come back, no? So this is missing here in the definition, exactly once, and let's call it more formally urine. Okay, so one should also reach to a starting vertex. So let's say you start somewhere, you start here, you go to this, you go to this, and then you go to this, but you can't reach to this particular node, right? This is, therefore this is not a linear graph. Any other graph, let's say this is, this is an Eulerian graph. Why this is an Eulerian graph? Actually, you can draw this Eulerian graph without lifting the pen, no? So if I start here, like these are my nodes, 4 nodes. So if I start at this particular position, I can actually draw like this, no? Without repeating anything, and that way I can reach to that particular position, right? Right. So this is a Eulerian graph, and you can identify that Eulerian graph has visually, except the start, right? So except the start place, you will always have even degree, right? If we, so each of the node will have even degree in Eulerian graph, maybe, okay, except possibly the start place. So if you remember, there was a graph called that Königsberg graph, right? Or Königsberg Bridge graph. Let's solve it. How do you draw it? Yeah. So the Königsberg Bridge, that graph, if you remember, that was not Königsberg Bridge, right? So in here, there are some places, 1, 2, 3, and 4, and then there are some edges, right? Bridge, there are bridge. So if you draw like this, then this, right? So this particular graph was not an Eulerian graph. So if you start traversing, no, so let's say I start traversing like this, then this, then this, then this, then this, and I stuck. Either I have to repeat an edge, or in this case bridge. Manu, which is which one? The this one, this graph you cannot reach. Which one? Left one or? Okay, let's check that now. So if you draw like this, maybe this you can draw, right? But you cannot draw this one if you have the middle one. If the middle diagonal is there, you may not draw. But this you can easily draw, right? And this has, what is the degree of each of the node? So this is 1, 2, 3, 4, 5. This is 5. 1, 2, 3, 4. This is 4. 1, 2, 3, 4, 4, 3, 4, 5, 5. Any question on this? Can we draw this or not? Is this a Eulerian? No. Why it is not an Eulerian? Because you cannot reach to that place, right? So if you start at some point, let's say you start A, B, and C, and D. If you start A, you may not able to reach at A, because the thing is, it's, you can only do so if you have even degree, right? So why it is even degree is required? Because when as long as you enter, you need to go out from there. If you can do that, then that is Eulerian. Otherwise, it is not, right? So in the Königsberg example, that is also not a Eulerian. It is also not Eulerian, right? Because here also the degrees are not matching, right? So here the degree is 3, 3,
Sir,
3, 1, 2, 3, yeah, 4, 5, 5. Yes.
sir, in the left one, the graph you have drawn, if you will remove that semicircle in the left, then it will be Eulerian graph.
Yes.
No, sir, that
This
first graph you
one.
have drawn.
This one, yeah. So here also, if you draw, like if you remove this,
Yes, sir. Now it is Eulerian.
yes. Because now 1, 2, 3, 4, 5, right? So now you can actually draw like this, then this one, and then this. No, how will you draw this? Okay, then this, yes. No, even this you can't draw, no? Can you draw?
Yes, sir. You can start from.
Yeah. But if I draw like this, I'm gone, no?
Sir, draw a straight line, then again the semicircle, then again a straight line.
A straight line, semicircle.
No, no, sir, that up above one you have drawn now. After that, draw a straight line coming down, then draw a semicircle.
And then,
Then
yeah.
you draw.
And here the degree is 1, 2, 3, 4. Here 1, 2, 3, 4. Here 1, 2, 3. Right, and this
Sir, you
one.
have to reach starting point, then you have to draw one more edge.
Right. So starting point you are not reaching, no?
Sir, you can draw one more straight line from this that three node.
Yeah, this one, if you draw like this, then you will reach starting point and then the degree will be 4, 4 for them. Yeah, yeah. So you can just exercise with this, but the major thing is you need to traverse all the nodes. Oh, sorry, all the vertices, all the edges, and without repeating edge, right? So that is, and you should reach to the starting point. Then that is a Eulerian graph. Um, and the Eulerian graphs have certain properties in terms of degrees, right? So that is important to know. So just give me a minute. So here one of the important thing is like every node has degree even, right? Why that is true? Because that you should understand like this: if you are going in this edge or in this node, you need to go out from this, right? So if you are going in, you need to go out as well. So the degrees of each of these nodes are, so the in degree of this node. So in degree means you are, let's say, coming in from somewhere, and out degree means if you are going out, that should be same. So in degree and out degree should be same, and therefore the degrees of each node should be even for Eulerian graph. Okay. The other one is slightly related, but it's called Hamiltonian graph. And the Hamiltonian graph is here, instead of visiting every node, right? You visit every vertex. So this is called Hamiltonian graph. Hamiltonian graph is a graph which so is a graph where is a graph where one can visit all the vertices without repeating any one of them. Starting node. Right. So, for example, this graph, let's say if this is a graph, yeah, so this graph is a Hamiltonian graph because I can visit all the nodes at exactly once, right? I visit all the vertices without repeating any one of them. I can start at any point and I can reach at that point without repeating any of the vertices, and I can visit all of them, right? So you can think of graphs which are Hamiltonian but not Eulerian, and vice versa as well. So leaving those things for your thinking exercise. But Hamiltonian graph is a graph where you can visit all the vertices without repeating any one of them, and you can come back to the same starting point, right? So a starting point when you go, so it is not counted as visited twice, right? So this is like go here, 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 and here. Of course, you are visiting starting two times, starting node, but that's fine. Okay. So except starting vertex, you don't have to repeat any of the node. So any other graph like this. Well, you can repeat the edges, no, but you should not repeat vertices. Can you do that? So can this be a Hamiltonian graph? This is a Hamiltonian graph, right? One can easily say this is an Hamiltonian graph, because what I can do is I can start here. I can go to this, and then I can go to this, then I can go to this, and then I can go to come back to this, right? So this is a Hamiltonian graph. I don't have to actually visit all the edges. I don't care, but only thing I need to do is visit all the vertices. Okay, so this is just a brief introduction. This is not like something which is in detail we need to discuss in the course. The separate course on graph theory covers these things in a much more detail. But here we are just at least you should have an understanding of what these definitions are and what they mean. Okay, now we'll move to graph coloring. So graph coloring, we have seen very briefly in one of the lecture what is graph, what do we mean by graph coloring. But here let's start with some motivation actually to know graph coloring and know the application from the application point of view. So there are these timetable things, right? So we all like have to make timetables for different things. For example, timetable for your classes and all. So let's say there are certain things like there are different courses. Okay, so let's draw that first. So there is a course on this M4C, right? Then there is a course, let's say, called graph theory. There is a course on operating system. Then there is a course on not compiler, let's call it computer network. And then there is a course on maths. Okay. So these are different courses which are offered in IIT Jodhpur. Now let's say there is some rules associated with this. Students, there is no student who is taking both M4C and computer network. Okay, so these two things are like there is no overlap. If there is no overlap, we will not have an age. Okay. So the question is, so what is happening is there are some rules like the thing is M4C and graph theory no one is taking together, let's say, but M4C and operating system people are taking together. Operating system and computer network also there are some common students. Maths there are like every student is taking maths, so there are a lot of common students and everything is like every student is taking maths, so maths has a common students with all the courses. Graph theory has a common student with, let's say, operating system. So if there is some common student, I am drawing an age. If there is no common student, there is no age between those two nodes, right? Now the thing is, in this graph, now can we say like how many so distinct hours are required to offer this class? Let's think like this. So let's say there is only one classroom. Okay. There is only one lecture hall, and in this lecture hall you have to run all these classes. Okay, and this is in physical mode. So now in this class, if this is the scenario given, how many hours is required to run this class? Let's say your class starts at 8 a.m., 8 to 9, 9 to 10, right? 10 to 11, 11 to 12. Worst case, if you don't know graph theory, what you will do is just different so floats will make them oh sorry, there is not just one classroom. Maybe let's say there are more classrooms. LH, sorry, yeah. So let's say there are more classroom LH1, LH2, and LH3. Let's say there are 3, 4, and 5 classroom. Let's say, right? 1, 2, 3, 4, 5. So there are 5 classrooms. If you don't know graph theory, what you will do is you will run the classes in different timings, right? Maybe 8 to 9 I will do. So if I don't know graph theory, I will do M4C 8 to 9. I will do OS 9 to 10, right? I will do graph theory 10 to 11, and I will do computer network 11 to 12, and I will do maths 12 to 1. Different classrooms I will assign, and different timing I will assign. But this is not efficient utilization of time, right? You can easily see that some classes can happen together, some classes cannot happen together. For example, I can always do M4C and graph theory parallel, right? There is nothing, no one is stopping me to use because this is, I'm taking 1, 2, 3, 4, 5, 2, 3, 4, 5 hours. How much minimum time I can do this classes so that all the students can attend their classes? Anyone? 3, right? So in 3 hour I can actually do, because why 3 hour? Because M4C and graph theory, they are totally independent, right? Graph theory is, no one is taking M4C together, but C and no one is taking together. So all this can be assigned to 8 to 9, right? So let's look into this. So I can do M4C and graph theory and computer network, all classes together. That's from 8 to 9 a.m. Right? But since I have done 8 to 9, can I do operating system 8 to 9? Cannot be, because then the students of M4C cannot attend. So I have to do it separately, 9 to 10 maybe, right? Can I do maths 9 to 10? No. Maths also I cannot do 9 to 10, because there are some operating system students. So I need to do it 10 to 11. And in 3 hours, I have done all these 5 courses, and there is no conflict, right? So no 2 students having same time classes. So if you look into this connection of graph coloring, this has an analogy with the graph coloring problem, where instead of this hour, right, 9 to 10, 10 to 11, I can have a color, right? So I can have a color like 8 to 9, 10, I will say red, 9 to 10 green, 10 to 11 blue, and 11 to 12 yellow. Now the problem is graph coloring, and the minimum number of colors required to color this graph, right? So that's the question. So how many minimum number of colors is required to this color this graph, so that the adjacent vertices do not have same color, right? Because adjacent vertices do not have same color, and this is exactly called graph coloring problem. And in the graph coloring problem, what we need to make sure that we need minimum number of we need to find minimum number of colors, so that the adjacent edges, adjacent nodes do not have same color. Okay. So we will see one particular algorithm for graph coloring today, that is called greedy algorithm. Greedy algo for graph coloring. Okay, so just give me a minute. It's just very simple two-step algorithm. The first step is color first vertex with first color, right? So you have so what is given? Let's even before that, you have given the set of colors, right? Set of colors. Let's call it R, G, B, Y, and so on. Right? So set of colors is given, and a graph is given. These are the input, and the output of this algorithm is number of colors required, right? Number of colors required for graph coloring. So what are the steps? The number one step is color any vertex with first color. First color. So any vertex you choose in the graph and you use any of these color, the first color, let's call it R. And then what you do is you have to do following for the remaining p minus one vertex. Do the following for remaining b minus 1 vertices. Right? So assume that you have p vertices. So let's call it p minus 1 vertices. What do you do? Consider the currently picked vertex and color it with the lowest number color. Okay. So let's call it A. Consider the currently picked vertex and and color it color it with the lowest number color. So we'll see what this number mean with the lowest number color that has not been that has not been used, okay, on any previously colored vertex in colored any previously colored vertex adjacent to it. If all previously used colors appear on the vertices adjacent to P, assign a new color to it. Okay. If all previously colored, previously used colors used colors appear on vertex vertices, let's call it vertices adjacent to V, right? Then assign new color. Yeah. So very simple greedy algorithm, but it works really well in practice. So you have this RGB, and so this can be also numbered 1, 2, 3, 4, right? So anytime you look into the edges, right? Sorry, you look into the nearest the neighbors, and based on that you decide, right? So first First step is you choose, so anything you have to color. Let's say I have a graph like this. Okay. This is my graph and I have to color it with using different color. So first thing I will do is I will choose any of the vertex and I will color it with a first color available, which is in my case red, right? So I can use red for coloring. Let's say my first node is this, right? Then you choose any of the vertex again, right? Because you have a p minus 1 vertices. And in any of these p minus 1 vertices, uh, you can choose the same color, right? So can you maybe, so whatever is available. So let's say my next vertex is this one if I have choose. So now what are the, so since none of the neighbors are colored, I can again use red for this, right? I can use red for this because none of them are colored. Now next, let's say I have chosen this one. Now since I have chosen this one, I can easily see that my neighbor has already used red. So I cannot use red. I have to use the next color. And in this case, the next color is green for me. Right, next color is green for me. So this is I have done. Now let's say my next node is this one. Now since again my neighbor has already used red color, so I cannot use red, but I can use green, right? So I can use green here also. Since my neighbor has used red, so I can use green here also. If I choose, I can use green. Now here what can happen if I choose this one, right? Since my neighbors have used red, I can use green. Now here, my neighbor has used red, my neighbor has also used green, so I cannot use both of them. I have to use the next one, whichever is available, and that is yellow in my case, right? And that's what I use and color it. So this completes the algorithm, and this is giving me that you require 3 color, right? So question here, does this algorithm gives you a correct solution? Correct, I mean to say the minimum number of color required always or not? Okay, so that is a question and that we will discuss maybe tomorrow. So tomorrow we also have a quiz. So maybe we can do some discussion and then we will jump to quiz. So, so tomorrow, the question is for tomorrow is this algorithm which I have just described, right? Which is a greedy algorithm. Does this algorithm always give a correct solution? That means the minimum number of colors required to color a graph or not, right? So we'll discuss this tomorrow. And any question on this particular theorem or particular algorithm? Sir, do we choose a color and traverse the whole graph? I didn't get. So in this algorithm, you are not doing that, right? Yeah, so here in this greedy algorithm, you are just choosing a node, right? You are choosing a node and just looking into neighbors, you are deciding. That's all. So the graph, like nodes, you can choose, right? So the nodes you can choose in a linear order. So you have just all the nodes available. You choose any of the node. You can start. You have a liberty to start at any of the node. Only you have to make sure that your neighbors have not used the same color. If your neighbors have used the same color, then you have to use the next available color, right? So if your neighbors have used all have used the some color, then whichever is next available you use. So you are not really traversing the whole graph. No, Not really, right? So you are just choosing any of the random node and deciding best ones. But will it work always? And in what example it does not work? So you'll see that tomorrow. So we'll stop here. Tomorrow we will have because Saturday we are following Friday this week, right? So tomorrow we will have a lecture. What we will do is maybe 30 minutes we will take a lecture, then a 5 minute break, and then quiz. Okay, and the quiz will be on the graph theory, whatever we have covered in this week. Any question? No. Okay.